Welcome to my YouTube channel. My name is Vasant S. Naik from Government First Aid College, Kumta. Now we are in the first session of the Unit 1, Frames of Reference, prescribed by Karnataka University, Dharwad for BSc first semester. In this video, I am going to explain you the definition of frames of references, events, and observers, inertial and non-inertial frames of references, Galilean relativity, and how to derive the expression for Galilean transformation equations. Let us first define the frame of reference. An event can be located with reference to some coordinate system is called the frame of reference. Here we need some coordinate to specify the position of the object, and those coordinates may be Cartesian, polar, or spherical. Suppose if we are standing in a room, if we want to specify our position, we can specify our position from the left wall or the right wall, or we can specify our position from the roof. Therefore, we need some coordinate to specify our position. If the particle is moving in a space, we need some coordinates to specify its position. At the same time, we need the time, that is at which time that event takes place. Now let us discuss about the definition of the event here. There's something that happens in the space at particular point and time is called an event. Therefore, an event is completely defined by location and time. For the term observer, specify the reference frame from which a set of objects or events being measured. For example, if you take one reference frame here with Cartesian coordinates x, y, and z, here is the observer who is at the point O of the reference frame. The observer may be at any position. But now we have taken the observer at the origin of the coordinate system x, y, z. So this is the frame of reference for this observer who is at rest. Now this is one event. Now we can consider it as a particle, we can consider it as a vehicle, or we can consider as another observer. Suppose if now we have to take this event, and this event or the object is moving. Now we can locate its position, and this is the another particle which is moving. So look at the difference here. The particle which is moving very slowly and the particle which is moving very fast. No doubt, both travels the same distance, but how can you differentiate them by telling one is moving very slowly and another is moving very fast? That's why we need another coordinate. That is, we need time. Therefore, these two events we can define by its location or the position, and also we can define that event with respect to time also. That's why we need to define any event by taking consideration of the position as well as the time. Now the observer who is observing these both events, we locate those two events with respect to position and the time. And if we take another example here, take the another reference frame. Okay, this is the another reference frame here, and a different event. In this case, what happened? The observer is moving, and at the same time, the particle is also moving. Now we have the two observers. Observers who is at rest is observing this event, and the observer who is moving, he also observes this event. For one observer is at rest, another observer is moving and is watching this particular event. So both the observers locate its position and they specify the time of that particular event. Remember, in classical physics, the time is absolute. Means the velocity of the particle is very low compared to the velocity of the light, because we are discussing about the classical physics here. Therefore, here all the events are, or all the events velocity is very low compared to the velocity of the light. That we have to remember. And also in classical physics, time is an absolute quantity. That is, time is same in both frame of references. Which are those two frame of references? One frame of reference which is at rest, and another frame of reference which is moving with a uniform velocity. Here the frame of reference is classified into inertial frame of reference and non-inertial frame of reference. Let us discuss one by one. Here, first one is inertial frame of references. A frame of reference in which Newton's first law and second law holds good is called inertial frame of reference. Otherwise, the frame of reference subjected to inertia is an inertial frame. Otherwise, we can define it as the frame of reference at rest or moving with uniform velocity along a straight line is an inertial frame. That is, inertia is nothing but the object continues to be in the state of rest or in uniform motion unless an external force is acting on it. So this is the frame which is at rest, and the observer is also at rest. The rest is the inertial condition. Is the another frame of reference which is moving with a uniform velocity. So both are inertial frame of references. That is, the first frame of reference is at rest and the observer is at rest. The second one, the frame of reference is moving with a uniform velocity, and also the observer is moving with a uniform velocity. Both these frames are called inertial frame of references. So the second one is non-inertial frame of references. The frame of reference under acceleration is called non-inertial frame. Otherwise, therefore, a coordinate system moving with either increasing or decreasing velocity along a straight line or under rotation is a non-inertial frame. That is, in case of the inertial frame of reference, object is moving with a uniform velocity. But in this case, what happened? This frame of reference is moving with a increasing velocity or decreasing velocity. That is, the frame of reference is not moving with a uniform velocity, it is moving with different velocity. That is, velocity is not a uniform. It may accelerate or it may de-accelerate. Otherwise, the frame of reference may rotate, and this condition is called non-inertial frame of reference condition. So what is the condition here? The frame of reference must be the increasing or decreasing velocity along a straight line, this one, or under rotation, this inertial frame of reference is under rotation. So these frame of references are called non-inertial frame of references. Now let us discuss about the Galilean relativity. The fundamental laws of physics are the same in all frames of reference moving with constant velocity with respect to one another. It's the Galilean relativity. Now let us derive and define one of the important relation Galilean transformation equations. What is the Galilean transformation equation here? The transformation of coordinates of a particle from one inertial frame of reference to another frame of reference is called the Galilean transformation equations. This is the actual diagram you have to draw and the examination. But in order to understand the Galilean transformation equations, let us discuss part by part. To have a frame of reference S, which is at rest, O is the observer, and here is the particle P. Now we can locate the position of this particle with respect to the observer O. So this is the coordinate of this particle. This particle have to specify its position with respect to x-axis, with respect to y, and with respect to z-axis, and at what time the particle is at the position of the P. That is, you have to specify where is the position of the particle, or what is the position of the particle, and when the particle is at that particular position. XYZ defines the location or position, and T defines at what time the particle is at that particular position. Now the particle is along the x-axis. Therefore, the particle is at a distance x from the observer. That is, if we consider x-axis as a road and a car is at the point P, observer O is standing on the road and he is watching the car. The car is along the road, that is, it's moving along the road, and its distance is x from the observer. And the car is not moving along the y-axis. It is not moving in the upward or downward. It is not moving along the left side of the observer or right side of the observer. It is moving farther. Therefore, its displacement is x. Therefore, coordinate of P with respect to observer O is x, y, z, t is the given by the distance OM is equals to x. Now let us actually define the Galilean transformation equation by taking these two frames of references. One frame of reference as at rest, another frame of reference S dash, moving with uniform velocity, that observer O and O dash are at the same point. This is at time t equals to 0. Both the frames of references are at the same position at time t equals to 0. Then the frame of reference S dash moves with a velocity v, and at the same time the particle P is also moving with a velocity v. Therefore, here x, y, z, t is the coordinate of the particle P with respect to the frame of reference S. X dash, y dash, z dash, t dash is the coordinate of the particle this P with respect to the frame of reference S dash. That's why I have to take coordinates x, y, z, t and x dash, y dash, z dash, t dash, because one frame of reference is at rest and observer is at rest. He is watching the particle which is moving with velocity v, and another observer O dash is also observing the particle p which is moving with velocity v. Here observer O dash is also moving with velocity v. Therefore, the coordinates changes x, y, z, t for O, x dash, y dash, z dash, t dash for O dash. Now, with respect to the observer O, the particle P is at a distance x at the time t. At particular instant t, this is the position of the particle P for the observer O. And x dash is the position of the particle P to the observer O dash. That is, particle P is at a distance x dash from the observer O dash. Particle P as a distance x from the observer O. Therefore, coordinate of T with respect to observer O, x, y, z, t is OM is equals to x. Coordinate of P with respect to observer O dash, x dash, y dash, z dash, t dash is O dash M is equals to x dash. Now, let us concentrate here. The observer O is at rest and he is watching the observer O dash who is in the frame of reference S dash. That is, observer O dash is moving away from the observer O with a velocity v, and displacement of the observer O dash is from O to O dash in time t. Therefore, this is the velocity. That is, for the observer O, velocity of the S dash is v is equals to O dash by t. That is, here the displacement is from O to O dash in time t. Therefore, velocity is equals to displacement upon time. We can write displacement OO dash is equals to V into T. Therefore, OO dash is the displacement of S dash. This is given by V into T. So, from the diagram, here the length O dash M is equals to OM minus OO dash. Therefore, O dash M is x dash, OM is x, and OO dash is v. Therefore, here x dash equals to x minus vt. Therefore, this is the transformation of coordinates of a particle from one inertial frame to another inertial frame. This is called Galilean transformation equation. Now, the particle is not moving along the y, or it's not moving along the z axis. Already give an example of the road and the car. For the particle is not moving along y and z axis. Therefore, y dash is equals to y and z dash is equal to z and t dash equals to t. I already told you in classical physics, the time is absolute. That is the observer O and the observer O dash are observing the event at the same time. That's why the t dash is equals to t. This is the Galilean transformation equation. X dash is equals to x minus dt, y dash equals to y, z dash equals to z, t dash equals to t. Therefore, Galilean transformation equation allow us to transform the position of an object or event from one frame to another frame. Let us take one example here. Here a person is inside the train. Now, the person inside the train, let us remember here that I need your concentration at this point. The train is in the moving condition. The person who is inside the train is moving. That is, with respect to this particular observer, the train is at rest because he is inside the train. All the windows and doors are closed. So with respect to him, train is at rest and is moving inside the train through a distance of 5 meters in 5 seconds. Therefore, observer who is in the train, he displaces through a distance of 5 meters in 5 seconds. Let us take another observer who is at rest. We can consider him as the frame of reference which is at rest. He is watching that event in the particular time here. Now the train is moving with a velocity of 0.6 meter per second. Let us watch the same event, this event here, which I have mentioned in the top. There is this observer is at rest. This observer is in the moving condition and the train is moving with a velocity of 0.6 meter per second. Now to find out the displacement produced by this observer with respect to himself, and we have to define the position of this observer with respect to the observer who is at rest. Now the observer is moving, who is in the train, and the train is also moving. The person who is inside the train travel the same distance which I have mentioned in the top. And the person who is at rest is also measuring the distance traveled by the person who is in the train. Now both persons are taking the measurement. The person who is in the train is moving. His displacement is same 5 meter. That we have taken as x dash. And the observer who is at rest is watching the same event. He also measures the distance traveled by the person who is in the train. Now the x dash is 5 meter because distance from one end to the another end is 5 meter here. Now let us find the distance measured by the observer who is at rest. So according to Galilean transformation equation, x dash equals to x minus vt. We have taken x dash is equals to 5 meter. And here x dash is equals to formula. What is the formula? X dash equals to x minus vt. And this observer is in the train, which is moving with velocity of 0.6 meter per second, and he travels this distance in 5 seconds. Now to find out the distance x, there is this distance you have to measure. What is the distance here? X is equals to x dash plus vt. What is the value of x dash? X dash is 5. What is v? 0.6. T is 5. So what's the value here? X equals to 8 meters. Therefore, the distance measured by the observer who is on the ground and who is at rest is 8 meters. That is, person who is moving, he measures his traveling distance as 5 meters. But another observer who is at rest is watching the person who is inside the train. He measures his displacement as 8 meters. Get the difference here. But the distance measured by the observer in the train and the distance measured by the observer who is at rest is also correct. Both measurements are same. Measurement by the moving observer and the measurement by the stationary observers are same. That's why this Galilean transformation equation allows us to transform the position of an object or an event from one frame to the another frame of references. Thanks for watching.